Planets orbiting the nearest stars offer the best possibilities for future detailed studies of planet structure, formation and evolution. The closer the systems are to the Sun, the more feasible becomes the characterization of their planets. The latest discovery from the Red Dots project is of a multiple planet system orbiting our low-mass stellar neighbour, GJ887. What are these planets like, and what can we learn from such a nearby system? Let's explore those questions right now. Think about when we move to a new house, a new city, new town or new neighbourhood. Once settled in, we want to learn as much about those around us as we can. We try to join the local community, introduce ourselves to the neighbours, walk around taking in all the sights, getting to know the neighbours, trying to find out where we fit within our new surroundings. With the Red Dots project, we are doing just that, but on a cosmic scale. The Red Dots initiative was born out of the Pale Red Dot project, the work that led to the discovery of the nearest planet to the solar system, Proxima b. Go check out the discussion with Dr. Miko Tuomi on Proxima b, the link is in the description below. But with Red Dots, we are mapping the planetary systems of the nearest and coolest stars to the Sun, and the focus is on the smallest stars, the M-dwarfs, which are the most abundant stars in the galaxy, accounting for around 60% of all stars. Now, being the end of the stellar sequence, M-dwarfs range in physical size from 0.6 to 0.1 times that of the Sun, and the mass is similar. In fact, in many ways, the stars can be broken into two populations, early Ms and late Ms. So early Ms are stars that are the more massive subset, the hotter stars with temperatures ranging from 4,000 to 3,000 degrees Celsius, and interiors that are similar to the Sun, where the core transfers energy by radiative diffusion and the upper envelope transports the energy by convection. Similar to how a boiling pot of porridge brings the heat up from the surface from below through circulating cells of hot and cold material. And around the middle of the spectral sequence, M4, M5, so M's run from M0 to M9, the increasing depth of the convective envelope reaches the centre of the star, removing the partial radiative envelope and changing to a fully convective star. The lowest mass stars down to the hydrogen burning limit are fully convective and seem to represent excellent stars to search for planets, since the small mass means our methods for searching for planets allows smaller masses to be reached for a given orbital period. However, another way they separate themselves from their earlier brethren is that they also tend to rotate faster on average. Here we show the distribution of rotation velocities, with on the x-axis we have v sin I, which is the equatorial rotation velocity of the star, but projected onto the sky, so there's a sin I component where I is the inclination given our line of sight. And so stars that are highly inclined are going to have much higher rotational velocities than we measure here on Earth. We can see that the solid histogram and the red curve represent the early M-dwarfs, and the dashed histogram and the green curve represent the late Ms. Clearly we can see that the early Ms have much smaller rotational velocities when compared to the late M stars. Now this may not sound problematic if one set of stars rotate at speeds of 1 to 2 kilometers per second, whereas another rotate at 8 to 10 kilometers per second. But the radial velocity method that we use to detect planets and measure their masses has problems with faster rotating stars. Therefore there's a balance here between the slightly higher mass earlier Ms that rotate slowly and the lower mass Ms that rotate faster. The star in question here is one of these early Ms, an M1V star, and is located at a distance of only 10 light years, very nearby indeed. The star has a mass of half that of the Sun, an optical V-band brightness of 7.3 magnitudes, so not too far from being visible to the naked eye, and it's a slow rotator, with a rotational velocity of only 2.5 kilometers per second, meaning it is magnetically inactive, and so an excellent target in the search for planets. With red dots, we use the radial velocity method, which makes use of the Doppler effect for light, an effect where a source that moves emits light at a different frequency than a stationary source. The frequency also depends on if the object is moving towards us or away from us. In this case, if a star is moving towards us, the frequency of light is shifted to higher frequencies, whereas if it is moving away from us, it's shifted to lower frequencies. The problem is how to measure the effect, and we do that by breaking the star's light up into its constituent colours, which allows us to see the star's chemicals. We use a spectrograph for this work, and the spectral lines give us markers of the frequency of the light, and we can then compare those frequency positions over time and watch the wobble of the star's velocity, which tells us if there's an orbiting companion gravitationally dragging the star around an orbit. For GJ887, we found at least 2 low-mass planets orbiting the star. The first, GJ887b, has an orbital period of 9 days, and with a velocity amplitude of only 2 meters per second, its minimum mass is only 4 times that of the Earth. Yes, remember, these are minimum masses, not absolute masses, since we do not know what the inclination of the system is to our line of sight. Highly inclined systems can boost the planet masses significantly. But when we consider the random alignment of planetary systems in the cosmos, their minimum masses tend to be fairly close to their real masses. The second planet in the system, GJ887c, orbits the star in only 22 days, and with a Doppler velocity amplitude of 3 meters per second, the minimum mass of this planet is 8 Earth masses. We can see these planets are orbiting very close to their star. Their years are both less than 22 days, which is very different to what we find in the solar system, where here, Mercury is the closest planet to the Sun, with an orbital period of 88 days. In fact, compact and low-mass planetary systems orbiting smaller stars seems to be a common outcome of the planet formation process. The occurrence rate of such planetary systems, coming from both radial velocity surveys and transit programs, appears to be somewhere around 2 to 3 planets per star, meaning all M dwarfs are orbited by a system of low-mass planets, an incredible finding for sure. Another intriguing fact about this work is that there appears an emerging third Doppler signal in the data, which, if confirmed as real, will relate to a planet orbiting the star with a period of around 50 days. Now, being further out, this would place the planet in the liquid water habitable zone for GJ887, which is the shell around the star where an orbiting planet like the Earth could maintain liquid water on its surface. Both GJ887b and C are too close to the star, meaning it's too hot for liquid water to exist on their surfaces. It would evaporate too quickly. Now, this work was led by Dr. Sandra Jeffers from the Göttingen Astrophysical Institute in Germany, and the results have been published in Science magazine, so go check out the paper. So there we have it, another neighbour opening their doors for inspection. The solar neighbourhood is growing all the time. GJ887b and C add to the nearby planetary systems we already know to exist orbiting small stars. Planets like Proxima b and C and Barnard's star B. What more secrets do these nearby systems hold? Who knows? But GJ887 is bright enough, for example, that in the near future we can attempt phase curve observations of these planets. Observations that would allow us to thermally map the planets around their orbits and understand the heat distribution around the planetary atmosphere, if indeed they have any atmospheres. This could allow us to model cloud patterns, wind patterns and more. And so with the current crop of really nearby systems, and those other nearby systems that are currently hiding, orbiting small worlds, this is an exciting time to be studying the stars on our cosmic street.